Hi everyone, I'm Faro Abdulfatai Odeji. I'm a subsea and flow assurance engineer with Federal Intermediate Service, Lagos, Nigeria, and I'm here to speak on this research that I carried out with my lecturer, that's Kazim K. Salami, that's Doctor, a senior lecturer from the Department of Chemical Engineering, Ladoke Akintola University of Technology, Oyo State, Nigeria. And the topic is flow dynamics and temperature distribution of a typical T-junction pipeline using computational fluid dynamics. This is a great honor to have this presentation at the annual meeting here of the American Institute of Chemical Engineers. And I'm speaking right now from Lagos, Nigeria. My objectives of this presentation are to study the flow dynamics and temperature distribution of a typical T-junction pipeline using the CFD, then analysis of the fluid behavior considering a circulatory system. So for this particular research now is the T-junction pipeline with two inlets and an outlet. My introduction proper now. T junction is just a pipe component. It's one of the pipe components used for pipe configuration. This configuration is useful in either splitting or mixing fluid depending on the purpose of the installation really. Then we have this particular research as the cold and hot fluid enter through each of the inlets, two inlets, while the mixing and the heat loss can be observed at the outlet of the T junction pipeline at controlled inlet velocities. I need to say this work is actually an extension of a research done by a particular group from ANSYS Fluent Images YouTube groups. They did the research by using hot and cold water mixing for cell and published it in 2015. However, this is an extension of that work in which the original work failed in convergence test and the results from the simulation were not actually correct. So this study will conduct a mesh dependent study on this simulation before the results of the simulation will be presented and analyzed. So it's an extension of the work and the result is more acceptable and more reasonable now. The application and study. So applications, one of the areas where T-junctions finds its applications, okay, that should be fine there. Finds application is in nuclear reactor where it is used for mixing of cold and hot streams to reduce the temperature of the discharge stream in a nuclear plant reactor. Another application is where there are being contributions towards advancing research on this pipe configuration. You know, like I've said earlier, T junction is a type of pipe configuration, and such as the thermal load threshold that can lead to fatigue. So there has been a tremendous research in trying to make this a breakthrough in trying to look at the thermal load threshold that usually leads to fatigue in this type of configuration. The study part of this research is that temperature fluctuation as a function of different thickness of pipe. So the so-called temperature behavior in this pipeline is fully and largely dependent on the thickness of the pipe and mixing inside the D junction too. So the mixture that is occurring in the pipeline, in the T junction pipeline, and also the thickness of the material that is used for the pipe are really a major factor for the temperature fluctuation. And of course, the geometrical change influence on mixing as well as its temperature, the turbulence and temperature too are key factor here in considering the pipe configuration with respect to the temperature fluctuation. The behavior of the fluid also at this junction is important due to turbulence as a result of fluid interaction and safety consideration as a result of turbulence experienced. Ideally, fluid will always be turbulence. Laminar flow, we have the laminar, we have the transient, and we have the turbulence. So in this regard now, we are setting it at the particular temperatures. You know, I said earlier, we have two inlets and an outlet. So these two inlets are set at different velocities, different velocities of move, you know, for the fluid to move. Then there is that junction where they meet before they now comes out from the outlet. So certainly there is turbulence involved in this research. The mathematical models of T-junction, the history of building up a mathematical model is long, really. There are some approaches how to model fluid flow in the T-junction. For mathematical model as consequently defined coefficients which describe the T-junction. So there's a Miller branches, or what we call the T junction branches by Miller. So what this does basically is just that the marking of the T junction branches by Miller is depicted by you can see it from the image here. Now you have two defined coefficients, which is K31 and K32 for dividing flow, and also K13 and K23 for combining flow. So you can see from the diagram as well, we have the um the first one named this, we have the point 1, point 2, and point 3 respectively. Then also here, so we have the relationship that we try to establish the mathematical model for induction, and you can see the quantities of the, you can see the relationship where you have the, for the K31 you have the V, where the V is the velocity, the mean velocities. Then we have then the V1, V2, and V3, right from the mathematical relationship we have there. They are the mean velocity at each branch, and the H1, H2, H3 are the statistic pressure heads after subtraction of the friction losses at each branch. The problem of this mathematical model is that these coefficients have no physical meaning. So that's the setback with respect to mathematical model of the T junction. So they are not loss coefficients because their values can be less than zero. So that's basically the reason why they have no physical meaning, really. The methodology of this research is basically we use popular and commercial software, ANSYS, to develop the model, to do the analysis, and also to report the result. So for the model development, we have geometry that was designed from the ANSYS workbench, or what we call the ANSYS design modeler. Using the ANSYS design modeler with measurement, and the material was actually a structural steel, and we consider water as the fluid flowing. So it has two inlets, like I've earlier said, for cold and hot stream respectively. So there is a inlet one which is for cold, and inlet two which is for the hot stream respectively. So now defining the boundary conditions for this. So we have the table here that represent the values that were the parameters that were used for the simulation. So we have the velocity of hot inlet to be 0.5 meter per second. We have the velocity of the cold inlet to be the 0.4. So you can see there is a reduction in the velocity from each side. So they didn't move at the same velocity. That's for a reason. Then we have the temperature of cold fluid, which is at 27 degrees Celsius, and the temperature of the hot fluid at 100 degrees Celsius. So these are just ideal situations that we try to set here just to read what we could have from the simulation. Then we have the diameter of the T junction pipe to be 0.5. Then we set the acceleration due to gravity to be 9.8. Yeah, so the turbulence model that was used was the K epsilon realizable, and the work function was not equivalent non function. So these are just what we adopted when we got to the part of the pre-processing. We are in ANSYS in ANSYS simulation. Sorry for that. We have the pre-processing, we have the solution, and the post-processing. The pre-processing, that's where we talked about the development of the model, the geometry. We use CAD to develop the geometry. Then you do your meshing, you do your different analysis there before you get to the, that's where you set your boundary conditions too, right? Then before you now go to the solution. Yeah, so the creation of the model here, like I've said earlier, we use the design modeler to have it. Then we develop our model in 3D. Then from there we do the body sizing just to have a suitable our aim really is for proper convergence and exact numerical results at the end of the simulation. And here we set the inflation just to have a proper representation, and when we are going to have the mesh. And the other part here, the right hand side, we have the mesh. Now meshing is a very huge process and a very important factor when it comes to convergence, especially when you are talking about computational fluid dynamics. it plays a lot, and that's why you have the study, the mesh independent study, and also we have what we call the grid independent and the grid dependent study with respect to how you want to monitor and how you want to see it really. So behavior of the velocity and temperature profiles of the streams, both at the inlet and outlet of the junction, were studied and presented as we move on. Now we what we did from the what we did from the simulation after setting up the parameters, having our scenario set, our boundary condition and everything. When we got to the solution, then we try to read and we had some difficulty in obtaining the result. Then what we do is to do the mesh independent study. So what we do by the mesh independent study basically, you just to go to you go to our mesh, then you readjust, you've been probably reducing the mesh sizes, and you want to agree with me that these are hugely dependent on computational strength, on the power of your computer. So the more your computational strength, the more you can have the fineness of the mesh, and the best and more durable your result could be will be. So for the result discussion, so basically we have the accuracy of the simulation, which is very important. Okay, I must say convergence in CFD is very important, and it is actually the main target of every CFD simulation. So if a numerical method can satisfy the two important properties of consistency and stability, so we generally find that the numerical procedure is convergent. So what I'm trying to say is that convergence depends on two major factors: consistency and stability. So when dealing with CFD codes, there are three important aspects to abide by for iterative convergence. So we look at all the you look at all the discretized equations, such as the momentum, the energy, etc., are deemed to be converged when they reach a specified tolerance at every nodal location. So when I talk about nodal, I mean the node and element. When you are talking about the discretized, that's the meshing part. Now you have different meshing sizes, then you talk about the nodes where the mesh and the element too. Then the second point is that the numerical solution no longer changes with the additional iterations. So these are the factors, these are what you should look out for. Then the third point is overall mass, momentum, and energy and scalar balances are obtained. So if these three factors are achieved, and you should note that during this numerical procedure as well, the imbalances, that is the errors of the discretized equations, are monitored, which we have here with the ANSYS. Yeah, ANSYS, that's what we call the RMS. So other software to have their ways of monitoring the imbalances, and these defects are commonly referred to as the residual of the system of algebraic equations. So that is they measure the extent of imbalances, that is the extent of error arising from this equation, and terminate the numerical process when a specified tolerance is reached. So that speaks a lot about how important our convergence and residual and tolerance, or what we call residual and convergence tolerance, are with respect to simulation, general CFD simulation really. So that's why we are trying to reach out from the solution here. Also, now from our result, we have the accuracy of the simulation, and also the second one, which is the scale residual of the simulation. Here it is expected that the residual decreased with increase with number of iterations until there is no further change in the residual trend with increase in number of iterations, and that's what I depicted in the first image we have here. Like I've said earlier, that your what we call convergence is hugely dependent on two factors: the consistency and stability. This must occur. The convergence and stability must occur. And I made mention of the residual also, the residual, and that's what I have here in the image. That is the image that is named 2A here. So when you talk about the residual and the convergence tolerance, so it is recommended it's recommended according to school of thought and research and standard that the scaled energy residual decreases to a recommended convergence tolerance of about maybe 10 raised to minus 6, while the scalar species may need to only decrease to a convergence tolerance of about 10 raised to minus 5, or what we call 10 exponential minus 5, to achieve energy and species balance respectively. So these are the working principle, the working techniques that has to do with convergence when it comes to CFD, and that's what we try to achieve here. So we couldn't achieve from our research, we couldn't achieve the result of, if you look at the green trend there, it's almost achieved. That's our list, and that's about -3. That's 10 raised to power -3, or 10 exponential -3. So we couldn't achieve the 10 raised to exponential -5. However, some school of thought and some research accept that once you could achieve 10 raised to 10 exponential -4, your result is as good to go too. However, we were able to maintain a consistency. You can see at a particular point, at a particular iteration level, we were able to have consistency in our result, and that's what we have here being on the graph on 2A. So you have the consistency. So once consistency was achieved, and this was hugely dependent on the mesh, we have to, we did a lot of mesh independent study where you go back to the mesh, you readjust the mesh, then you come back here to iterate. Then also the second point, the scale residual of the simulation, which depict the relationship between the nodes of the force. Now the example, our model here is a force and the number of iteration. So these are very key. The nodes and the nodes and the of the forces. So it's very key. So what we are trying to say is that we try to check the relationship of the maximum of the force value with the number of iteration, and you can see at a point we maintain consistency as well. And like I've said, for you to know your convergence, it has to have consistency for stability. Now, however, I must state that converged solution does not necessarily mean an accurate solution. I think this is very, very important, and that's why we have different solution errors. So that has to also be into consideration, and so we were able to achieve this, and this is a far better result than what was really achieved from the original research, and this is an advanced work, and so these are my results. These are our results from the research, from the analysis. So also we have the trend of temperature and velocity, because we want to check the variation of temperature as well. So the result that shows here depict that at the outlet, the fluid interaction showed that there is an increase in mixing of the two streams at the junction. So we can see that as being depicted. So like I've said, this image, this particular model is a faucet. So we are using an example of a faucet model where we have the two inlet and the outlet, and these are our analysis give us the interaction for the temperature and velocity at on the T junction pipeline. Now also for the velocity distribution, so similarly for the velocity also, we can see the highest velocity was observed at the outlet section, and at the outlet section of the T configuration, the maximum velocity at the junction was 0.9 meter per second, while the input velocities from the hot and cold inlet were 0.5 and 0.4 meter per second respectively. Like I already said that from our parameters that was setting for the model. In conclusion, so from the numerical investigation to the internal flow analysis of mixing cold and hot water in two inlets and one outlet T junction, the following were deduced. So we have it that there is a loss of heat up to 66% at the T junction with respect to cold stream, while the heat loss increased in the length of the outlet geometry. So at a point we try to increase the outlet of the geometry, and we realize that the more we increase, the more the heat loss. The heat loss increased with it as well. So there was an increase also in the velocity at the T junction more than the summation of the two velocities of the two inlet streams. So these are our observations, and these are our conclusions as well. However, this work is still subjected to further work. This research is still subjected to further work. There is still need for verification and validation through either experimental method or analytical method. The analytical method I've started already, and I look forward to make this a full paper journal with my verification and validation with my analytical method. For the experimental method is quite expensive to set up, and we look forward to if you can partner with a good laboratory where we could carry out the experimental method. For further mesh independence, or what we call the grid, or what we call the grid readiness study to improve the solution accuracy and reliability. So there is need for us to probably still check further. Well, this hugely dependent on the computing capacity. So it has to be it depends on the computational strength of the computer really, and this will be go a long way in contributing and making the result more accurate. So I have my references here. And for any further question about this particular presentation, you can contact me via this different platform, and I'll be really expecting to have to have the conversation with you with regards to this research, the input, the corrections, the critical analysis and the likes. They are well welcomed and well welcomed and well expected. Thank you very much for your time.